طيب بسم الله الرحمن الرحيم. Welcome to ch8.4. Can you hear me, Shabab?
Yes, doctor.
Okay.
Yes.
Welcome to ch8.4. So today's lecture will be the 24th, and I just want to make a couple of announcements. So the first one is homework 3 has been postponed, and inshallah it's due Thursday at 11:59. The quiz 4 will be inshallah tomorrow. The coverage will be 7.1 to 7.6. Okay, so let me just go over what we did so far in this chapter. So we started talking about natural and step response for parallel RSA circuits. Remember, we had the we stated that we want to consider the circuit where you have resistor, capacitor, and inductor. So it turns out there are two possible configurations. The first one is in parallel. The second one is in series. So we started with the parallel combination of R, L, and C, and we saw that we have either overdamped, underdamped, or critically damped responses. So for each damped response, they have the same general form of solution, but there are some special cases of each type of response has its own general solution for that reason. So to differentiate or to characterize responses, we need to know the relation between the Nibber and the radiant frequency, the resonant and Nibber frequency. So the resonant frequency is omega naught, which is 1 over square root of LC. The Nibber frequency is 1 over 2 RC, and both of them, they have a unit of radians per second. So depending on the relation between them, we can have either overdamped, underdamped, or critically damped response. Okay, so when we started this chapter, we started with the natural response. We said that, well, when we were deriving the natural response, we were concerned about the quantity that's common, because we know for sure that I and V, the currents and the voltage, should be all zero. Should we eventually reach zero? So let's focus on the quantity that we are interested in, and that's the differential equation that we derived. And when we talked about the step response, we said that because they are in parallel, so eventually the capacitor will behave like an open circuit, the inductor will behave like a short circuit. So if you have anything that's in parallel with a short circuit, the voltage across it will be zero. So the voltage eventually will reach zero, but the current need not be zero. So in this case, we kind of like concerned about the current of the inductor, because that's the quantity that's going to be sustained for a long time. And we derived the differential equation. If this point is confusing you, so it doesn't matter. It's always, we have always this form of solution. If we have an overdamped response, then the quantity that we are interested in equals to the final value of that quantity multiplied or added to it these two terms. If we have an underdamped, we are always going to be interested in the final value plus the remaining two terms. If you have critically damped, we will also have to know the final value and plus the quantities that have been added to it. So that's basically what we did. We have some sort of systematic way of solving problems, and we are interested in parallel RLC circuit. Now you may ask yourself, okay, the other configuration, what should we do with it? The series RLC circuit. It turns out that the derivation, that everything is almost similar. There's only one single difference here, which is the Nibber frequency. And let's see what the value of that Nibber frequency. So let's derive the natural response of series RLC circuit. So what we need to do, we need to first apply KVL. So if we apply KVL, we have the voltage across the capacitor, R multiplied by I, the voltage across the inductor, L di by dt, plus the voltage across the capacitor, which is the integral of the current passing through the capacitor, plus V naught equals to 0. So if this is a mix, there's a mixture between integration and differentiation. So let's actually differentiate both sides so we ensure that we have a differential equation. So if we differentiate both sides, we will end up with R di by dt plus L di squared by dt squared plus 1 over C I equals to 0. So let's put it in the standard form. Standard form is a form where the highest derivative has a coefficient of 1. So if we do it like this, we divide both sides by L. So we have okay, this is a differential. This is a differential equation that we actually need to solve. And if you recall, when we talked about the parallel RC circuit, we had the following differential equation. So if you recall, the differential equation was something like this. So as you can see, that the only difference between there's few differences between the differential equation in the RLC, in the parallel RC, and in the series RC. So it seems that we're interested in the voltage and in the parallel, and we're interested in the current in the series, but this is not very important. The important factor is this coefficient here. This is the only difference between if we write it in terms of like a dummy variable x, then this one will look like then we know for sure that in this case A is 1 over RC, B is 1 over LC. If we're talking about for series RLC circuit, we have A is actually R divided by L. B is 1 over LC. So 1 over LC is what? Omega naught square, right?
Yes.
Okay. So 1 over C is omega naught square. So we can see that omega naught square is actually the same. It doesn't change. What's going to change is alpha here. If you recall in the previous case, is alpha is actually A divided by 2. Because if you recall, alpha was 1 over 2 RC. And in this case, alpha is 1 over 2, R divided by 2L. So that's the only thing that's going to change. Other than that, everything is exactly the same. So they have the same characteristic equation. So the characteristic equation, if we are to solve for it, we will end up with S squared plus R divided by LS plus 1 over LC equals to 0. This is for series So now let's see what's going on. Well, it's exactly the same form of solution. The only difference here is alpha. So we're expecting the same roots. We're expecting the same behavior, exactly the same behavior, with slightly different values for the roots. But the behavior the overall behavior is exactly the same. So we'll have an overdamped situation when alpha is greater than omega naught. We will have an underdamped situation when alpha less than omega naught, and we will have a critically damped response when alpha equals to omega naught. Okay, واضح يا شباب? Is it clear? Is it clear, شباب? Any question?
Yes.
Yes, go ahead. أحمد.
الدكتور عند الالفا لما ما طلعت لي الفا الصفحه اللي قبل هذه اقدر اني اقسم على 2.
We don't have alpha here. We have A.
But what about if I divide by 2?
You divide by 2, which one?
For the both sides.
Then you will end up with the same form of solution. If you divide everything by 2, then you will end up with the same equation. So if you have an equation, then you scale both sides by the same factor, then you will end up with the same solution.
Okay, thanks.
Any other questions, Shabab? Okay. So let's try and solve this problem. This problem is kind of like, well, I think at this stage we probably like master the way of solving second order circuits. So what we have in here, we have a 0.1 microfarad capacitor, and this one was initially charged to 100 volts. Then at t equals to 0, the capacitor is discharged through a series combination of inductor and resistor. So what we want to do, we want to find I of t for t greater than 0. So what should we do, Shabab? Fahim?
We should start by finding A and omega naught.
Alpha, not A. Okay, exactly.
Okay.
So let's start by finding actually the alpha and omega naught. And why do we need to find alpha and omega naught for him?
To decide which response do we have, is it critically damped or overdamped?
Yes, exactly. So we'll have 100 millihenry, 560 ohm. So alpha in this case is R divided by 2L. So 560 2 divided by 100. Alpha is 2800 radians per second. So if I square it, it's going to be 0.0784 and 10 to the power 8 radians squared per second. Omega naught squared is exactly the same as the previous case. So we can easily So clearly what type of response we have here? Salman?
It is underdamped.
It's clearly underdamped. Yes. So the solution is of the following four: I of t, okay. So what we are missing here, we're missing B1 and B2, B1, B2 and omega naught, I'm sorry, omega D. So omega D is simply the square root of omega naught minus alpha squared. And in this case, we have 9600 radians per second. Now, in order to find B1 and B2, those quantities depend on the initial condition or the initial conditions. So what is the initial value of the current here? It's not given in the question, but what's the initial value of the current? Salman?
I think it is 0.
Yes, why?
Because the switch was open.
Yes, because we have an open circuit.
Yes.
Exactly. So the initial value of the current is 0. And remember, if you substitute, this one should be equal to B1. So B1 is 0. Now, in order to find the other value here, we need to actually, in order to find B2, we need to differentiate the current and evaluate it at 0. So to differentiate the current, or this current is actually the same as the voltage across the inductor divided by the inductance. So what is the initial voltage across the inductor? Looking into the picture. So what is the initial voltage across the inductor? Ahmed?
Also 0.
Why?
Because of the open circuit.
Okay. Ibrahim? The same?
Because there is no current flowing in.
Okay. Wait. Okay. Okay. Very good. Very good. The issue here is your answer is incorrect. Yasser?
Yes, the current is 0, so we will have 0 voltage in the resistor. So basically, we have 100 volts in the inductor.
Exactly.
They will be in parallel.
Exactly.
Or in the same circuit, yeah.
Exactly. So the current is actually 0, right? Because the current has to be continuous. Cannot change instantaneously. So meaning that the voltage drop across the 560 ohm will be 0, because the voltage drop across the 560 ohm is the current multiplied by the resistance. Now what's left is actually, we have this voltage, 100 volts here. If this one has a 0 volt, it means that all voltage drop will be across the 100 millihenry. You can show that by applying KVL actually. If you apply KVL at T equals to 0 plus, you will see that minus 100, because this is the voltage across the capacitor, so the capacitor cannot, the voltage across the capacitor cannot change instantaneously. Then you will have the voltage across the inductor, this one. Then you will have the voltage across the resistor multiplied by the resistance. Since this current is 0, so VL should be equals to V naught should be equal to 100 volt. واضح يا شباب؟ Okay, so in this case we have it used to be actually minus alpha B1 plus omega D V2, but B1 is 0, so we ignore it. That's why we ignore it. So B2 now is actually and it's something around 0.104 amperes. Therefore, the current is actually B2, which is 0.042, e to the power alpha, negative alpha, which is e to the power alpha, which is negative alpha 2800, sine omega d, which is 9600 t amperes, and this is true for t greater than or equals to 0. Ahmed?
دكتور ممكن ترجع شوي اللي طلعت فيه الكي في ال.
Yes. Yes.
دكتور انت جبت الفولتج حق الاندكتر صح؟
Yes.
هل يساوي سالب 100؟
لا. minus 100 plus VL equals to 0, which means VL equals to 100.
minus 100, yes.
Now, okay, the second part is asking us to find the voltage across the capacitor. So what is the voltage across the capacitor? We have two options actually to find the voltage across the capacitor. Rahim?
I think we can use 1 over C, the integral of the current plus the initial value of the voltage.
Yes, exactly. That's one option. 1 over C, 0 to T I d tau plus the initial voltage, which is 100. Or you can apply KPL. VC is actually VL multiplied by VR, which is in this case VL is L di by dt. VR is actually, if you're not comfortable with the integration, VR is I multiplied by R. So you need to differentiate and multiply it by the inductance to get the voltage across the inductor, and add it to the voltage across the capacitor, the resistor. This is KVL. Anyhow, if you use either of these methods, you will end up with VC of t equals to 100 cosine 9600 t plus 2917 sine 9600 t multiplied by e to the power 2800 t. The unit is volt, and this is true for t greater than or equals to 0. Any question, شباب؟ واضحة؟ Clear? Okay, let's see what. So we can solve as many problems as we want. The way of solving problems here is exactly similar to the previous case, the case where we have a parallel RLC circuit. The only difference here is we need to be careful about the initial conditions and the initial conditions as well as using the right form of alpha. Now let's study the step response. Remember, the natural response is like, it's called the discharging response. So there used to be a source, and the source is removed. Natural response, the step response is the opposite. It could be, there could be a situation where you previously had a source, then you added another source. So at the end of the day, you will have one source that exists in your circuit as after the switch being open or closed for a long time. So let's see what we can do with this one. If we apply KVL here, we will get minus V plus I multiplied by R plus L di by dt plus Vc equals to 0. So if I write everything, because at the end of the day, I know the current will be eventually 0, because after the switch being closed for a long time, the capacitor will behave like an open circuit, and the current passing through an open circuit is actually 0. So I need to write everything in terms of I, in terms of the voltage across the capacitor. So I is the current, which is the same as the current passing through the capacitor. And you remember the current passing through the capacitor is dVc by dt. And if I differentiate this one more time, I will get C dV square C by dt square. So if I substitute, I will end up with something like this. dV C square by dt plus R divided by L So if you recall, this is exactly the same form as the natural response. The only difference here is we have an homogeneous differential equation. And if you remember what we did with this situation last lecture, when we talked about the step response of parallel RLC circuit, we said, well, the solution will be exactly the same. The only difference here is that we are going to consider the final value. So if we have an overdamped response, then the response will be the final value plus whatever response that we used to have for overdamped. Similarly, if we have an underdamped, we'll have the final value plus whatever response we used to have for underdamped response. And if we have critically damped, it's going to be exactly the same. So again, you can think about this this behavior as the standard form, and the natural response as a special case where VF approaches, where VF is 0, where the final value is 0. Any questions, Shabab? Okay, let's try to solve this problem. So we used to have a circuit without a switch. Then at t equals to 0, the switch been closed. So what we want to do here, we want to find the voltage across the capacitor. Okay, so let's start by so what's the standard way? What's I mean the standard way of solving such a problem? Hadi?
Specify the if it's underdamped or overdamped or critically damped.
We need to, yes, exactly. We need to characterize or categorize the response. So let's start with drawing the circuit and knowing what. For t greater than 0, we have a 48 volts. We have 0.1 Henry. We have 280 ohm resistor. And we have 0.4 microfarad. So alpha, since we have a series RLC circuit, R divided by 2L, and in this case is 1400 radians per second. Alpha squared will be 1.96 times 10 to the power 6. Omega naught squared will be 25 times 10 to the power 6. So clearly here, omega naught is greater than alpha, alpha. So we have a critically damped, we have underdamped response. So if we have an underdamped response, we know that the solution is going to be the final value. Since we have step response, the final value plus P1 Okay, so what's missing here? We don't know the final value. We don't know B1 prime, B2 prime, and we don't know omega D. So let's start with phi final. So what's the final value here? What is Vc as t approaches infinity? Ibrahim?
Maybe 48.
Exactly, 48. So when the switch been closed for a very long time, the inductor will behave like a short circuit, the capacitor will behave like an open circuit, and we will have a 48 volt across the capacitor. Okay, so what about omega D? Omega D is actually omega naught squared minus R, and if we solve for it, we'll end up with 4,800 radians per second. Okay, now we need to find P1 prime and P2 prime. So in order to find P1 prime, we need to actually substitute t equals to 0 in the general form of the solution. So we'll get P1 prime, and we know that what's the initial value of the voltage across the capacitor from here? Ziad?
0.
Exactly, 0. So the initial value is 0. So B1 prime is minus 48 volts. Now we need, in order to find the other response, or in order to find the other variable, we need to differentiate the voltage with respect to time. And evaluate it at 0. If we do that, we will get minus alpha V1 prime plus omega D V2 prime. If we solve for it, we'll end up with V2 prime equals to minus 14 volts. Okay, now we found all the variables that we need, or all the coefficients that we need, so we can easily write down the solution. So the voltage across the capacitor is going to be 48 minus 48 cosine 4800t minus 14 and this is true for t greater than 0. So let's see if this solution makes sense. So we know that by looking into the circuit, we know that the final value should be 48. So let's take t equals to infinity and substitute. So if we take t equals to infinity here, take the limit, then we see that the exponential term will be 0, and so we'll end up with 48. Now the initial value, we know that the initial value is 0. So if we substitute t equals to 0, we'll see that we have the first term is constant, so it will be there. The second term, evaluated at t equals to 0, it's going to give us minus 48. And the third term, evaluated at t equals to 0, is giving us 0. So 48 minus 48 is 0. So this one is clearly the solution for this problem. Any questions about? Okay. Let's pause for 1 minute before we start the new chapter or the last chapter. Any questions, Shabab?
Doctor, can you go back to the circuit?
Yes.
Why did we say that P1 prime is negative 48?
For any differential, any initial value problem, you will have a differential equation like this. So in order to uniquely solve for this problem, you need actually, I need to give you the initial value, the derivative of the initial value. Okay? Otherwise, you will have infinite possibility of solution, infinite number of solutions. Okay. Looking into what we have in here, so we know that the quantity X is the voltage, right, across the capacitor.
Yes.
Okay. So we derived the solution for this one. We show that the solution for the voltage is VF plus P1 plus. So we need to evaluate it at 0. If you evaluate this solution at 0, this one, you will see that you will end up with VF plus P1 prime, صح?
Yes.
And this one should be equal to the initial condition of the voltage across the capacitor, which was 0. واضحة؟
اي واضحة.
Okay, excellent. طيب, now let's start with chapter 9. And chapter 9 is kind of like we are going to somehow shift gear here. So if we let's recall what we did in this course. So we started with definition of the voltage, the current, the power. Then we moved to resistive circuits, and we saw how to simplify circuits using parallel and series combination. Then we studied systematic ways of solving circuits using mesh node and all of these methods in chapter 4. Then we said, well, let's now consider two circuit elements and let's study the temporary behavior of these elements. So we studied the capacitor and the inductor, and we started with just like one of them in a circuit, either capacitor or inductor in a circuit with resistor. Then we said, well, what happens if we have both of them? And we kind of like classified the problem. We classified the problem into two sub-problems. The first one is whether we have a series combination. The second one is or parallel combination. And that's what we did. But throughout the whole course, there's one common thing among all of these circuits that we have. What do you think, sir? There is one thing common among all of these circuits that we've studied. Umar, muted.
Oh, sorry. Maybe trying to calculate the voltage and the current.
We always, whenever you have a circuit, we always, either in this course or even the last course in your undergraduate, you always need to solve for the voltage or the current, directly or indirectly. Ibrahim?
That the circuit element we have is ideal.
This is common, yes. We're still gonna assume this. Wael?
They are DC circuits?
Yes, exactly. All of the circuit elements that we have, they have DC source. All of the circuit elements we have, they have DC source. So now let's see what happens if we have something that DC source is a source that's constant with respect to time. What happens if we have something that's actually changing with respect to time? And let's start with a simple source and very useful source. It's called the sinusoidal source. So the source that we had is going to be of a sine or cosine nature. If you have a sine or cosine nature, then at time instant, for example, t1, the voltage or the current will not be exactly the same as time instant t2. If t1 is not equal to t2. If you have a DC source, then the voltage at time instant t1 should be equal to the voltage at time instant t2. That's why we have constant current with respect to time. For AC sources, we're considering the source that's actually alternating or changing its value with respect to time. This change could be something impulsive, something that's happened at a very short period of time then stay constant, or it could be something that has some repetition. In this case, if you have a sinusoidal source, then if you observe the voltage at t equals to 1, t equals to t1, then after specific time interval, you will see that this voltage will be exactly the same. If you multiply by that specific time interval, you will get exactly the same voltage and so on. So there's some sort of repetition associated with this one, or it could be any value, or could be any type of source. You see that if you have a digital system, for example, you have square wave, square sources. So sources are either on and off. On means say like 5 volts. Off means 0 volt, 5 volt, 5 0, 5 0, 5 0. But we will, in this chapter, probably in this course, and even like the sequel of this course, which is E213, you'll be focused on sinusoidal source. There's a very amazing reason why you need to focus on sinusoidal source. It turns out that, and you will see that in E207, if you give me any function, I can approximate it with multiples or with summation of sines and cosine at different frequencies. And this is something that you will see, inshallah, in chapter in E8 also. But just keep in mind in this course that we all what we're going to do is going to deal with is AC or sinusoidal sources. So what is a sinusoidal sources? Sinusoidal voltage is a voltage that if you plot it with respect to time, it has the following, it can be represented with the following equation. So let's dissect this equation, Vt equals Vm cosine omega t plus Phi, and let's analyze each component individually. So what is Vm here? Vm is the amplitude, which is the peak value here from the average. From 0 to Vm is the maximum value that the sinusoidal can reach. Then we'll have omega. This is omega, not W. Omega is the angular frequency. This unit is false. The angular frequency has a unit of radians per second. This is not the frequency that you are all familiar with. If you have a radio, then it's like it's 98 megahertz. This is not the frequency that you are familiar with. Related to it, something called the cyclic frequency, or F. F is the unit is 1/second, or hertz, after the German physicist Hermann Hertz. So we note that omega is 2 pi multiplied by F. Related to it's not specifically written here, but it's illustrated here. T is actually the period. Period is the time measurement. So it's the time needed for, if you think about it, this if you think about if you think about it this way, if you're standing here, then you're moving with the sinusoidal source until you reach this level. You calculated the time, the projection of time, your time movement, your movement in the time axis. You will see that this is called the period. And the period is actually related to the frequency by this relation. The last part is a part that's going to we're going to actually talk more about it, which is the phase, or alpha, not alpha, as phi, the phase angle. And note, if phi greater than 0, what does it tell you? If phi greater than 0, what does it tell you? Hadi?
That there is a shift
toward which direction?
Toward the left, the right.
We have a shift to the left. So if phi is 0, then you shift it to the left.
Oh, okay.
Okay, if phi less than 0, then there's a shift, but in this case, the shift is towards right. A very important note here that I want you to pay attention here. This alpha, or this, not alpha, this phi in the cosine omega t plus phi is expressed in radians, not in degrees. So in order to convert to degrees, you need to use okay. So in order to convert to degrees, you need to use this relation. So you take the value, you take the angle, multiply it by 180, and then divide it by pi, and this will convert the angle from radians to degrees. So radians is actually the actual unit. Degrees is going to give you like a better visualization of the angle. Any questions, Shabab? Before we move? Okay. Seems that this one is this topic is we are all familiar with. So now let's talk about something very important when we characterize an AC source. Ziad?
The period is always 2 pi for the cosine.
No, it depends on the argument. It depends on the argument here. If you have, what you're saying is you have cosine t, then the period is going to be 1 over 2 pi. The period is going to be 2 pi. Okay. So if this one is 1, then the period is going to be 2. However, if you have cosine x of t, then the period is not going to be 2 pi. It's going to be divided by x. Okay. حسن الصايغ في هذا question صح؟
ايه دكتور في الايكويشن حق الساينسويدال ويف احنا اتعلمنا في الفيزيكس ان المعادله تكون فيها كي اكس ماينس اوميجا تي بلس الفيس شيفت.
كي
اكس ماينس اوميجا تي.
Something like this.
Yes.
Yeah. It's a different convention actually.
Oh, okay.
But it's a cosine, so if you take it's an even function, so it doesn't matter. Okay. Good. طيب, a very important quantity, that we need to study is the RMS value. So whenever you have a sinusoidal source or an AC source, usually you're concerned about the RMS value. Let's actually derive the RMS value of that of a function of the sinusoidal source that we have, and then let's talk about the sinusoidal, the importance or the significance of the RMS value. So the RMS value of any function is you take the function, square it, integrate it over one period, then take the average over one period, then take the square root of 2, the square root of that. So remember, our function is, our signal is v of t. Our signal is the one that we want to find the RMS value of is given by Vt, Vm cosine omega t plus V So let's further simplify it. Let's assume that phi equals to 0 in this case. This assumption will not change anything. It will just simply simplify the calculation. Let's further assume that T naught is 0. Again, it's not going to change anything. It's going to simplify the calculation. So now we have everything we need. So let's integrate from 0 to t. Then we square it. Cosine square omega t dt. If we solve for it, we'll get 1 over t Vm squared divided by 2 plus Vm squared divided by 4 cosine 2 omega t from 0 to t. And you will see that this one is 0, so you'll end up with Vm squared divided by t. So why this term is 0? Because if you take any sinusoidal function and you integrate it over one period, so remember cosine square of alpha t, or cosine square of alpha, is going to be 1 plus cosine 2 alpha divided by 2. So if you take this term and integrate it over any integer multiple of a period, you will get 0. Think about it this way. What is the integration of a function? It's the area under the curve. If we have a cosine and we integrate it over one period, then we will get this area is equal to this area, and it's the opposite of that area, so that the total will be 0. If you take more than one period, integer multiple of periods, you will get 0. And in this case, we have 2. So that's why we're getting 0. Okay, now we calculated this one. Then the RMS value, remember, is the square root of what we calculated. So we'll get Vm divided by square root. So the RMS value is this one. And it's going only to change one thing here. It's going to change the amplitude. So if I ask you what is the RMS value, so what is the RMS representation of the source? Remember, our source is V of t, Vm cosine omega t plus phi. Then VRMS will not change the frequency, will not change the phase, it will only change the amplitude. Ahmed?
دكتور، لو افترضنا ان عندي داخل كوساين 1.25
1.25
يعني دور ربع.
No, the integral will not be 0.
تمام.
But remember,
دكتور وش معنات RMS؟
root mean square.
تمام.
Let's see why we're using this one. Why are we using root mean square? So what we want to do, we want to say like, well, I have an AC source, صح? Something that's sinusoidal, and I have a DC source. That's the two types of sources that I really have. So what I want to do, I want to find a point where I want to compare the average power. So the power could be positive or negative, depending on the relation between the current and the voltage. But I don't care, like, because I have a sinusoidal source, I don't care about the I don't care about the instantaneous power. So at t equals to 0, I'm getting, for example, this amount of power. At t equals to 0.1 seconds, I'm getting that amount of power. At t equals to 0.3 seconds, I'm getting that amount of power, etc. So there's some, because I'm having like a source that's changing with respect to time. So I'm assuming, or as a consequence of that, the power is also changing. But just keeping track of the instantaneous power is not something that's useful to me. So I'm concerned about the average. So what is the average power of a DC source? For a DC source, what is the power of the DC source? What is the power of this source? This is a DC source. What's its power? So let me move it here. So it's going to be P DC V squared divided by R, صح? From Ohm's law. This is we know. So what's the average of this one?
It's constant.
So what's the average of a constant?
Zero.
No.
لا
The same.
نفسه
The same value.
Yes. The average of the constant value is the value itself. So power DC is equal to now let's assume that I have this sinusoidal source, and in this case, let's assume I'm making it simple, so I'm assuming that the phase is 0, doesn't matter. So what is the power across this resistor? Again, using the Ohm's law, it's going to be V squared divided by R. V squared, it's going to be Vm squared cosine omega t squared divided by R. Okay, so what is the average here? So I need to find the average. In order to find the average, I need to integrate this with respect to time and divide it by the variable. And if I solve for it, I will end up with Vm squared divided by 2R. Okay, so this is the average. So now let's try to find a point, what value of the DC voltage that's going to give me the exact, what value of the voltage, what value of the DC voltage that's going to give me the exact same average power as an AC source. You see what I'm asking about? So what is V such that the two sources have the same average power? Clearly what I need to do is
Square root of 2V.
Yes. So what I need to do is I need to take the average of a DC, make sure that this average is equal to the average of an AC. In this case, the average of a DC is V squared divided by R. The average of an AC is Vm squared divided by 2R. So if I solve for it, I will get V equals to Vm divided by square root of 2. So the RMS value is telling me that if I tell you that the RMS value of a source is 100 millivolt or 100 volt, I'm telling you that this source is going to deliver on average. Remember, keep in mind this, on average, the same amount of power that a DC source with the 100 volt is going to deliver. Is it clear, Shabab?
Yes.
Clear.
Yeah, it's clear.
So what I wanted to do is I want to find a point of comparison between these two sources. If you have 220 volts in your home, it means that you have 22 RMS value. This is RMS value, which means that this AC source is going to deliver to you, on average, the same amount of power that a 220 volt DC source is going to deliver. Okay, let's take, I think we have 2 exercises, and then inshallah we will move to complex number tomorrow after the quiz. So what we have here is a very simple exercise. We have a sinusoidal source. The sinusoidal source has a specific frequency, specific phase, and specific amplitude. So the first thing that we are asked about is what is the period. Ibrahim?
We can take the value of omega, which is 120 pi.
Yes.
And omega equal 2 by f, or 2 by over t.
Yes, exactly. So t will be 2 pi divided by 120 pi, and this is going to give me 1 over 60. And this is going to give me 16.667 milliseconds. Okay, Walid, what is the frequency?
The frequency is 1 over t.
1 over t. So the frequency is 1 over t. And t is 1 over 60, so the frequency is 60 hertz. Okay, what is the magnitude of V at t equals to 2.778 milliseconds? So what do I need? Let's not focus on the exact value, but what do I need to find the magnitude? Ibrahim?
We need to substitute the time, but we first should change the value of phi.
Yes, exactly.
It's in degree.
Yes. So 30 degrees is equivalent to pi divided 180 times 30. And this is going to give me pi over 6. So then V of t will be 300 cosine 120 pi of t plus pi over 6. And it turns out that if you evaluate it at t equals to 2.667, this is going to give you the product of 120 pi with t is pi over 3. Pi 3 plus pi over 6 is pi over 2. What is cosine of pi over 2?
0.
0. Exactly. So the value is 0. But the last piece of information that we need is the RMS value of V. So what is the RMS value of T, Salman?
It is 300 over root 2.
Yes. 300 divided by square root of 2. So 212, 13 volts. Okay. So now, Ahmed, hold on to your question. So now let's see what's going on here. So we're asked to calculate the RMS value of triangular current. So remember, the RMS value that we found here is very specific for sinusoidal source. If you change the type of source, then you need to run the integration again. Okay, and we'll see what's the RMS value if we have triangular source. However, this is just an emphasis. This is just to emphasize that the RMS value depends actually on the source, on the source type. So how did we find the RMS value in the previous case? We took this is the formula for that. Then we integrate over one period. So if we have a triangular wave, triangular voltage, then we will have where to plot it. It will be something like this. Remember here the magnitude is IP, so the peak is IP squared. So what is the, it's going to repeat itself. So what is the, this is going to be T over 4, T over 2, 3T over 4, etc. So the integration is actually the area under this curve. So I'm taking the square of this one. So the integral of this is the area under that curve from 0 to T over 4. I'm sorry, from 0 to T. So in this case, you can see here that this area from here to here is exactly the same as that area, and it's exactly the same as this area, and it's exactly the same as this area. So instead of running the integral from 0 to T here, so let me run it from 0 to T over 4, and then multiply whatever value I'm getting by 4. So here I'm going to simplify it. Okay, so now what is the expression for I of t? What is I of t? So we want to find the equation of I of t here. So remember, the equation of a line is you need to find the slope and the intercepts. And if you do that, you will notice that for IP divided by t, and this is true from 0 to t divided by 4. Okay, now we found the equation, so I need to square it. So if you square it, you will end up with 16 IP squared divided by t squared multiplied by t, multiplied by small t. And this is also true from t. So now I have everything I need to solve for this problem. All what I need to do is actually substitute. And if I substitute, I will end up with 4 Okay, the RMS value now is going to be 1 over t multiplied by I p squared multiplied by t divided by 3. And in this case, we will end up with RMS equals to IP divided by square root. So if you have a triangular wave, then in this case, you divide the amplitude by square root of it. So you see that it depends actually on the type of wave. Okay, that's it for today. Thank you very much. We'll see you inshallah tomorrow. Just remember that tomorrow we have a quiz. It's going to be in the beginning of the class. The instructions are exactly the same as the previous quizzes. Then inshallah we will start. We will talk about complex numbers. Yasser?
Yes, Doctor, I did not get why the function of I is I squared.
The function of what?
IRMS is I squared, or the function inside the integral.
The function inside the integral, because I'm interested in I squared, because this is the definition of the RMS.
Oh.
You take the function, integrate it, square it.
Yeah. Yes, I get it now. Thank you.
It's actually root mean square. So you take the square of the function, then you take the mean, which is the average, then you take the root of that, which is exactly what we're doing. Okay, very good. Any other questions about? Okay, and just a reminder, most likely I will not hold office hours today. Ali?
Doctor, in the quiz tomorrow, will we draw the graph or not?
You will be what?
Will we draw the graph?
No. I know my limitation as an artist that I cannot draw, so I'm not expecting things that I cannot do.
Okay, thank you.
Yes, sir, question?
No. Thank you.
عمر؟
ايوه دكتور، في الهوم ورك اذا ما قال لي ان ايش الانيشال ستيت، هل يكون وش بالضبط؟
كيف ستيت؟
يعني بيقول لي مثلا على طول فايند في تي،
يس.
بس ما حدا ما قال لي ان السويتش كان مسكر من زمان ولا لا.
If the switch is closed at t equals to 0, we should assume that it wasn't closed for it was open for a long time.
ايه خلاص تمام، شكرا.